That's the same inequality we had here. I just made it more general, so it involves prices q prime and the fixed costs r instead. With other goods, it simplifies quite a bit. So this says we should buy a car instead of taking a taxi, or walking for that matter, if it's the case that the log of the price of taking the taxi divided by the price of driving your car per mile times the expenditure share for transportation is greater than your income divided by your income less the fixed costs. So this is something like the percentage by which taking a taxi per mile is greater than taking a car times the amount of your income you choose to spend on travel. If that thing's satisfied, or if that's greater than the percentage increase by which your income is greater than it would be if you paid the fixed costs, then you should buy the car. So that was a difficult sentence to express this equation, but the idea is actually pretty simple. Any questions about that before we forge ahead? Is this mechanically clear? No? Okay, so the recipe here, let me describe the recipe quickly. We know how to compute indirect utility functions. For a utility function like, where'd it go? Oh, we don't have it here. For this log utility function, we know how to compute the Marshallinian demands and the indirect utility function. In fact, maybe I'll just remind you, for these log utility functions, we just have something that looks basically like this, log of y minus something like alpha 1 log of p1 minus alpha 2 log of p2, something like that. So we know an indirect utility function. We think about two different states of the world, one in which you own a car, one in which you don't. You think about the income you have after paying fixed costs in each of those two worlds, and for each of the prices you face, whether it's the price of covering a mile, in this case, the cost of covering a mile walking, or the cost of covering a mile driving a taxi or buying a car, and just plug those into the same indirect utility function. So you're just evaluating this thing at different p's and at different y's. And then you see, so step 3, which one of those gives you a larger utility. And that tells you your decision. Yes, Wes?
So fixed costs always affect y.
Yeah, the way that's the way we're modeling fixed costs here. Yeah, that's right. You should be a little bit careful because for a case like this, converting income into expenditures per month. So this is a case where we're modeling a static problem here. If you think about buying a car, it's because you want to drive it for more than 1 month probably. So you should sort of convert it into fixed costs per month. So in this case, think about the cost of financing the car or something like that. We'll come back to that later. All right, are there other questions? Okay, let's keep going. So I want to switch gears and think now about how to aggregate demand across different consumers. So we've been thinking almost exclusively in our development of demand theory so far about the behavior of a single consumer. And we've gotten pretty far. We've said we thought about ways to characterize a consumer's preferences, ways to characterize the feasible set for a consumer, and we thought about how to solve the consumer's problem so that we can answer the question of what goods or how many goods of what sort a consumer will demand given prices and given income. That's really quite cool. Most of the times when we think about sort of policy problems, though, we're more interested in the behavior of a group of people than we are in the behavior of a single individual. And so that brings us to wanting to think about aggregate kinds of consumer demands. So here's a sort of statement of this. So we want to figure out what aggregate demand is for a group of people. So let's say there's a population of people is n of them. So in this room there's something like 90 people. And we're going to index these people by 1. So the person 1's name is 1, person 2's name is 2, and so on. And that can be m different goods. Okay. So the aggregate, I'm going to use a notation here. The demand for the jth person for the ith good is just x sub I super j. And it'll depend on prices and on income. Okay, now there's something important that we're sort of assuming here. People can have different incomes. That's why j is indexed by the person, right? So if I'm person 1 and you're person 2, I'm allowed to have a different income than you are. There's no subscripts on this p, though. So we're assuming to face the same prices. If we want to go out and buy a cup of coffee, it's assumed that we both have to pay $1.20. It doesn't depend on what our name is or other characteristics of ourselves. Okay, so then to compute the aggregate demand is just sort of blindingly obvious. We just add up all the individual demands. So the demand for coffee from everyone in this room is equal to the sum of the demands from each of us as individuals. And so all we do is just add up over all the people that we're concerned with, and that gives us an expression for the aggregate demand. We'll sometimes note that by writing a bar over the thing to sort of indicate total or aggregate demand. All right, so is that clear? It's extremely simple, but also important. Yeah. Yeah, it's a good question. So another thing you might interpret this, you might say, well, gee, maybe it's average. Sometimes we will express this in terms of averages here. This would be, if I could define, this is not what I've done there, but I could define it. Sometimes I might actually do this. I might define this to be 1 over n, sum j equal 1 to n of xij, p, yj. So this would be average demand. So it's just going to be different. This factor of 1 over n is the only difference. And sort of depending on what data you're trying to match up or whatever, choose one or the other of those. In applications, it probably depends on what data you have. We'll talk some about later, where we have data on aggregate gasoline demand for the U.S., for example. Okay. So then it makes us add up across the entire population. Other times you'll have data on what an average household does. Okay. All right, questions about this? This one's really easy. Okay, let's keep going. I want to do a little example here. So I've told you how to add this up for the general case of Marshallian demand, where you just have xi super j. But let's think about the case where we have a particular Marshallian demand, like the demands associated with the logarithmic utility we've been working with. So in that case, we have a Marshallian demand for the individual, which we're going to say is equal to alpha I. So this is the expenditure share associated with the ith good, and that's assumed to be common for everybody in this example, times income for the jth person divided by the price for the ith good. Okay, so is that clear? We're assuming here, in fact, that everyone's preferences are the same. Because they've got the same alphas, they've got the same log utility, but different people are allowed to have different levels of income. Okay, so that's just an example. In this example, then, if we go ahead and plug in this expression into here, we're summing now over all the individuals. And since alpha I and pi don't depend on j, we can factor them out. So we wind up with an expression here, which is equal to alpha I divided by pi times the total. Look what this is. This is the sum of income over all the j people. So it's just total income for the entire population. So if we're thinking about the E100 class still, it's the sum of all of your different incomes. Okay. And so that's interesting. That tells us that for these kinds of demands, at least, aggregate demand is just a linear function of aggregate income. So that's a useful property. It's not something which is satisfied for all preferences, for sure. This is a special property which is sort of satisfied sort of only for homothetic kinds of utility functions. But it's nice nonetheless. Okay, questions about that? Okay, let me ask quickly. we worked some last time asking about what the elasticity, what the income elasticity of demand was. So you'll recall, I hope, that somebody tell me an expression for computing income elasticities. Okay, that's good. So percent. Yeah. So one of these is percent change in demand for good one, we'll say, divided by the percent change in income. That's good. So that's one expression. We call that expression the arc elasticity. Give me one for a point. It's a point elasticity. Yeah, so there's a sort of counterpart to this is, in a way we'll often prefer to write this, will be something like dx1 dy, so the partial derivative of the demand with respect to income. And then to fix the units, this tells us something about the slope of the angle curve. That's what this is. To sort of fix the units, we'll multiply that by y divided by x1. So it's always, just visually, there's an easy trick here, which is you take the partial derivative you're sort of interested in, and then flip it over and get rid of the little partial derivative sign that gives you the expression for the point elasticity. Okay, so in this case, let's think about what the income elasticity is for a set of people having these preferences, so the aggregate demand looks like this. So in this case, what we have is x bar I equal to alpha I over pi times the sum over j people, j equal 1 to n of yj. And I'm just going to define this thing so that it's, I'm going to call this last part y bar. So I'm going to say this is alpha I divided by pi all times y bar, where y bar now is the total income for the people in the population. Okay, so what's the income elasticity of demand for this life good? We just need to compute a partial derivative with respect to y bar, I guess, here, and plug it in. So here we'll have eta is equal to, what's dx1 dy bar? What's the partial derivative of dx1 with respect to y bar? Yeah, so Hillary has it. So it's just a linear function. This is a very easy derivative. It's just alpha I divided by pi. And then we need to multiply by y bar in this case. And divide by the total value of x, so divide by xi bar in this case. We can simplify this, though. Does anyone see how? Oh, you mean here? Yeah, so that's right. So we've got an expression for x bar here that we can just plug in. Exactly. So from this, we know that this is equal to alpha I pi all times y bar divided by this thing, which is alpha I pi y bar. But, of course, this simplifies a lot and is just equal to 1. So the aggregate income elasticity, we said this last time, for individuals, if they have homothetic utility functions, we said their income elasticities are always going to be identically equal to 1. It's true for populations of people as well. So the income elasticity here is always going to be 1. It doesn't matter what the value of alpha is or anything else. If we have homothetic utility functions, we get unitary income elasticities. Okay. All right, so that's an income elasticity for these guys. I want to also talk about, I want to do one more thing before I move on, which is to talk about price elasticities. So using this same aggregate demand function, something we haven't talked about yet are price elasticities. So how would we define the price elasticity here? What would that look like? We sometimes use the Greek letter eta for income elasticities often. It's also a convention to use the Greek letter epsilon for price elasticities. So the price elasticity for the first goods, for example, what would that look like? It's just another elasticity. So the fact that we haven't talked specifically about a price elasticity doesn't change the nature of the formula we want to use. Yeah, just not explanation. We want a price elasticity of the demand function, but it is a straightforward substitution like that. Yeah, so this is an income elasticity because we're looking at the slope. We're looking at how demand changes when you vary income. Now we're going to think about how demand changes when you vary price. So instead of y's here, we'll just have p1. So epsilon 1 here will be equal to dx1. We want the aggregate one, so we're going to dx1 bar, dp1, and then here we'll have p1 divided by x1 bar. Okay, so that's the expression for the price elasticity. In this example, what will that be equal to? Okay, well, so what's dx bar dp1 or dpi in this general formula? We've got p in the denominator here, so it's a little more. This is going to be more interesting than the last one. So in this example, we'll have partial derivative with respect to pi will involve a minus sign, an alpha I, a y, and a pi squared. We have the pi in the denominator here, so we just use that ratio rule when we take the partial derivative. Oh, this should be a bar, sorry. Okay, so that's the partial derivative part. That's all times p. Sorry, I'm going to make this 1. That's all times p1 divided again by this thing. So divided by alpha 1, p1, y bar. Okay, so that's kind of nice. So what's this equal to? Some of this stuff cancels. This y bar cancels with this y bar. This alpha 1 cancels with this alpha 1. And what do you know? This p1 multiplies this p1 and cancels this p1 squared. And we wind up with the price elasticity here, which is equal to minus 1 for this case. Okay, so the elasticity, the lesson from this is not that all elasticities are 1 or minus 1. It's that the elasticities for the homothetic utility functions wind up taking this kind of very special form. Okay. Okay, questions? Yes?
Are price elasticities always negative and income elasticities always positive?
Oh, that's a good question. So let me take the second part first, and that's our income elasticity is always positive. So let's ask ourselves the question. The question is whether or not this always has to be positive or not. So what would be required mathematically for that to be negative? Well, let's first of all get a couple of assumptions out of the way. We'll assume that these are both positive numbers, so income is positive and total demand is positive. So then it boils down to a question about whether it's positive, whether this first derivative is positive or not. Can we have dxi dy be negative? Anyone know? So Hillary has an answer, and she says if it were negative, it would violate non-satiation. Okay, that's one possible answer. Are there alternative views? Yes.
There's some bits that are used for at lower
Yeah, so we haven't talked about this yet, I don't think. We may have encountered in another class. If a good is inferior, the definition of an inferior good is actually one where you consume less of it as your income increases. So, for example, I consume fewer ramen noodles now than I did when I was a grad student. And it's not because my taste for ramen noodles has changed that much. It's because I earn more money than I did when I was a graduate student. So the inferior goods will have negative income elasticities. In fact, that's the definition of inferior goods. We'll come back to that. The other question is, what can the price elasticity be negative? I want to table that one. I'll give you the short answer, which is yes. The longer answer is no. Okay. That's a little bit too coy. The answer is, in theory, yes. In practice, there's argument about whether that's ever absurd. Okay. All right, let's forge ahead. So I'm going to completely change. This is a, so it's, I have a half hour, so I'm going to really completely change topics. So we're still going to talk about consumer demand, but for the last several lectures, we've been talking about how the consequences of consumers when they maximize their utility subject to a budget constraint. And we've had, we talked about when they have different budget constraints, like in this modal choice problem, but they're always maximizing utility. I want to now think about a completely different way of characterizing the consumer choice problem, which mathematically is going to turn out to be extremely complementary to it. I mean, it's not. It will produce the same kinds of predictions. This is not an alternate theory of consumer behavior. It's just a different way to characterize it, which is often very useful. And so what we're going to talk about now is not thinking about consumers maximizing utility subject to a budget constraint, but instead we're going to think about a consumer solving a conceptually different problem, but one which is going to turn out to have a closely related solution. It's if I want to achieve a certain level of happiness, what's the cheapest way to do it? Yeah, that's the problem. And so it's called, more formally, the expenditure minimization problem. It's also sometimes called the dual consumers problem. And the problem we've been working with, maximizing utility subject to a budget constraint, is called mathematically the primal consumers problem. Okay, but that's just starting. Okay, so we've been working with this problem of maximizing utility subject to a fixed budget constraint. That's the primal problem. Here's the dual consumers problem. The objective function here, and you'll note you should be looking for some similarities. This duality. The objective function here bears a close resemblance to the constraint we had before. So this is just if there's two goods, the commodity space is x1 and x2, then the consumer's going to choose x1 and x2 in such a way as to minimize their expenditures. Okay, they're going to do that subject to a constraint, and the constraint is that they have to choose a value of x1 and x2 so that the utility they achieve is equal to some goal they set for themselves of utility of U star. So this is a consumer who sets a goal. He says, I want to be U star happy, and then goes out and figures out the cheapest way to achieve that level of utility. Okay, so that's formally how the problem is. All right, so let's go ahead and I'm going to show you how to set that problem up technically, and then I'm going to show you for the rest of the lecture and then some on Tuesday why this is a useful way to think about the problem. So I'm going to treat this here by setting up a Lagrangian because we've got an equality constraint, which is not as nice as it is in the primal case. But before I do this, let me show you something about the graphical version of this problem. So we're going to start off in the same space, commodity space that we've been working with, or that we're in the primal consumers problem, and we're going to have some of the same objects kicking around. So in particular, here's an indifference curve. Now I'm going to choose just one indifference. Well, let's see. We have multiple indifference curves. Here's another one. Okay, and this level of utility, this indifference curve is going to be associated with a particular level of utility, and I'm going to say that this one is the one that delivers a level of utility U star. Okay, now we've got a consumer. They're not going to take their income as given. They're going to figure out the cheapest way or the smallest income necessary to achieve the level of U star. So they're still going to choose x1 and x2 though, and they're still going to take prices as given. So if you like, what they're doing is choosing how much income they're going to need in order to achieve this level of utility. And how much income they're going to need is going to depend on the price they face. They're still going to have some kind of in the end they're going to have to pay for these goods they're consuming. So there's going to be a set of budget lines here with a slope of P1 over P2, just like before. But where before graphically we scooted around the indifference curve until we found a tangency with the budget line, here we're basically going to scoot the budget line around until we find a tangency with this special indifference curve. And so graphically what we're going to do is find a budget line. The slope is given because prices are given. And we're going to find the budget line that achieves a tangency with, given those prices, with this indifference curve that delivers this required level of utility U star. And so graphically this is going to be the answer to the problem, to the dual consumers problem of what's the least expensive way to achieve a level of utility U star. It's going to be to consume this quantity x1 star and this quantity x2 star. Okay. All right, so is that graphical setup there? Yes.
So it's going to be the point closest to the origin?
No, it doesn't. I mean, there are other points that are closer to the origin. It has to be tangent. Yeah, I mean, this is closer to the origin, I suppose, isn't it? Yeah. So the slope of the line is pinned down by prices because the consumer takes that as given, and the indifference curve is given as the consumer. They're not trying to change their own preferences, and so we're going to look at the tangency between the budget line and the indifference curve. That's going to pin down graphically the solution to the dual consumers problem. Okay. Now, here's how we can solve this thing mathematically. Here's an opportunity to share a Lagrangian with you, or actually properly a Kuhn-Tucker problem because we have an inequality. But anyway, so I'm going to define a function, script L, depends on prices and on U star. And remember, I had the problem I was trying to solve was to minimize expenditures subject to this constraint. And so I'm going to do my Lagrangian trick. I've got expenditures plus a multiplier, which in this case I'm going to call mu, times U star minus the utility we get from consuming x1 and x2.